Welcome to module 2 of chapter 4. The set of all integer solutions to polynomials of degree 1 is completely understandable. Next non-trivial case is set of polynomials of degree 2. In this module we are going to solve congruent equations. X square is congruent to A mod P, where P is an odd prime. Now in the process we are going to introduce or define quadratic residues and quadratic non-residues. We are also going to state and prove Euler's criteria for quadratic residues. In chapter 4, primitive roots and quadratic residues. In module 2 we are going to discuss quadratic residues and non-residues. The objectives of this module are introduction, examples and properties of quadratic residues and quadratic non-residues, Euler's criteria, Legendre symbol and its properties. Quadratic residues, it is defined like this: let P be an odd prime and A be any natural number such that GCD of A comma P equal to 1 if the quadratic congruence x square equal to A mod P has a solution, then A is said to be quadratic residue modulo P. That is, A is said to be quadratic residue modulo P if first of all the GCD of A comma P equal to 1, that is A is relatively prime to P or P does not divide A, and further it is a solution to x square is congruent to A mod P. Otherwise A is called quadratic non-residue modulo P. Usually whether A is a quadratic residue modulo P or quadratic non-residue modulo P, it is required that the GCD of A comma P should be 1. Two basic problems of quadratic residues are these. Note that if A is a quadratic residue modulo P, then A plus Kp is also quadratic residue modulo P for all k belongs to Z. Hence our proofs will mostly consider those A for which 0 is less than or equal to A is less than or equal to P minus 1. Now we will see the two basic problems of quadratic residues. The first one is, given a prime P, find all n belongs to n such that n is a quadratic residue modulo P, or finding all m belongs to n that are quadratic non-residue modulo P. Given a number n, finding those primes P for which n is quadratic residue modulo P, or primes Q for which n is a quadratic non-residue modulo Q. These are the two main problems which we are going to encounter, and we are going to try to solve these two problems. So one of the observation is, let P be an odd prime, then by definition a number A belongs to n can be quadratic residue modulo P only if GCD of A comma P equal to 1. Hence quadratic residues other than 0 are relatively prime to P. 1 is always a quadratic residue modulo any number n, as x square is congruent to 1 mod n always has a solutions 1 and minus 1 for all n belongs to n. Another example, to find quadratic residue modulo 11, we look at the numbers 1 square modulo 11, 2 square modulo 11, 3 square modulo 11 and 4 square, that is equal to 5 modulo 11, and it is easy to see that 3 is nothing but again 6 square modulo 11 and so on 10 square modulo 11. We are going to obtain 1, 4, 9, 5 and 3 are the quadratic residue modulo 11. Similarly, it can be easily verified that 1, 3, 4, 9, 10 and 12 are quadratic residue modulo 13. Note that in general, if P is a prime, then it suffices to square only the numbers 1, 2 up to P minus 1 by 2. As any x with P plus 1 by 2 less than or equal to x is less than or equal to P minus 1, we can find y belongs to 1, 2, 3 up to P minus 1 by 2 such that x equal to P minus y, hence x square is congruent to y square modulo P. So it is sufficient to consider only the numbers 1, 2 up to P minus 1 by 2. So it can be easily verified that two numbers x comma y belongs to 1, 2 up to P minus 1 by 2, then x square is clearly not congruent to y square mod P. Hence we have the following result. that is if p is an odd prime, then every reduced residue system modulo p contains exactly p minus 1 quadratic residues and exactly p minus 1 by 2 quadratic non-residues modulo p. Furthermore, the quadratic residue classes corresponds to numbers 1 square mod p, 2 square mod p and so on, p square p minus 1 by 2 square modulo p. So, now we are going to give an important criterion called Euler's criterion. Euler's criterion help us to find out whether given integer a, which is relatively prime to p, is a quadratic residue modulo p or not. So, it is an if and only if condition, that is, it says like this: let p be an odd prime, let a belongs to n such that GCD of a comma p equal to 1. So, up to this extent this is the hypothesis. Then a is quadratic residue modulo p if and only if a power p minus 1 by 2 is congruent to 1 mod p. So, Euler's criteria says that a is a quadratic residue modulo p, then immediately we have that a power p minus 1 by 2 is congruent to 1 mod p. That means order of a is less than or equal to p minus 1 by 2 in modulo p. So, the proof goes like this: suppose a is a quadratic residue modulo p, hence by definition the quadratic equivalence x square equal to a mod p has a solution, say that is x naught. As GCD of a comma p equal to 1, we get that GCD of x naught comma p is also equal to 1. Therefore, by Fermat's little theorem, we have a power p minus 1 by 2 is congruent to x naught square power p minus 1 by 2, but that is congruent to x naught power p minus 1 by Fermat's little theorem, which is congruent to 1 mod p. So, we got the required part, that is, if a is a quadratic residue modulo p, then we showed that a power p minus 1 by 2 is congruent to 1 mod p. Now, we will look for the converse. Conversely, assume that a power p minus 1 by 2 is congruent to 1 mod p. Now, we need to show that a is a quadratic residue modulo p. For that, we are going to use the fact that if p is an odd prime, then up is cyclic. As you recall that up is set of all integers which are less than p and which are relatively prime to p, that is group of units in Zp, and we know that up is cyclic, hence there exists an R belongs to n such that R is a primitive root modulo p. Now, since GCD of a comma p equal to 1, there exists a k such that a equal to R power k modulo p. Thus, we see that R power k into p minus 1 by 2 is congruent to a power p minus 1 by 2, but a power p minus 1 by 2 is congruent to 1 mod p, that we are assuming. So, hence we have that order of R p is equal to p minus 1, that divides, but order of R p is p minus 1, it is because R is a primitive root modulo p, but that divides now k into p minus 1 by 2. So, that therefore, k should be equal to 2 into j for some j, hence R power j is a solution of the quadratic equation x square equal to a mod p, as R power j whole square, which is equal to R power 2j, which is equal to R power k, is congruent to a mod p. So, we proved the converse part also. So, now onwards we are going to use Euler's criterion to check whether a is a quadratic residue or not, but still here we have to compute exponents of a. So, there we have some alternative methods also to evaluate whether given number a is a quadratic residue or not. Now, we are going to utilize primitive root, and its even powers are going to give quadratic residues and odd powers are going to give quadratic non-residues, that we are going to establish now. So, the proof of above theorem suggests that if R is a primitive root of an odd prime p, then set of quadratic residues modulo p is set to R power 2, R power 4 and so on R power p minus 1, and set of all quadratic non-residues modulo p is given by the set R power 1, R power 3 and so on R power p minus 2. So, this is one of the important applications of primitive roots. So, in a given odd prime, if you are able to find one primitive root, then it is possible to find out all quadratic residues as well as all quadratic non-residues modulo p. Further, it is easy to check that r power 2j into r power 2k, which is equal to r power 2 times j plus k. So, 1 is equal to r power p minus 1, as r is a primitive root, and r power 2j inverse, which is equal to r power p minus 2j minus 1. Hence, the set of all quadratic residue modulo p forms a multiplicative abelian group. So, not only this, we found there are how many quadratic residues are there. This is exactly these p minus 1 quadratic residues, they are also forming a group now. And further, if you observe r power 2j plus 1 into r power 2k plus 1, that is product of quadratic non-residues, we are going to get quadratic residue. Hence, product of quadratic non-residues is a quadratic residue. So, they are not closed under multiplication. So, they cannot form a group. Now, we will see that the product of quadratic residue and quadratic non-residue is going to be quadratic non-residue. So, that is r power 2j into r power 2k plus 1 is equal to r power 2 times j plus k plus 1. Hence, the product of quadratic residue modulo p and quadratic non-residue modulo p is quadratic non-residue modulo p. So, if you look at these quadratic residues and quadratic non-residues, they are behaving like multiplying plus and minus. If a 2 plus into plus is plus, like that here quadratic residues, product of two quadratic residues is a quadratic residue, product of two quadratic non-residues is quadratic residue, quadratic residue and quadratic non-residue is a quadratic non-residue. Now, we will see another important problem, that let p be an odd prime and r be a primitive root modulo p, then the product of quadratic residues is congruent to modulo p to r power p square minus 1 by 4, and the product of quadratic non-residues is congruent to modulo p to r power p minus 1 whole square by 4. The is very easy. So, the solution is for the part 1 first. By above observation, r square, r power 4, r power 6 and so on, r power p minus 1, r power all even exponents is set of all quadratic residues modulo p. Hence, we have r square into r power 4 into r power p minus 1, product of all quadratic residues, which is equal to r power 2 plus 4 plus 6 plus and so on plus p minus 1, that is equal to r power 2 times 1 plus 2 and so on p minus 1 by 2. So, that is equal to r power p square minus 1 by 2, p square minus 1 by 4. So, we got the required part for the first one. Now, we are going to prove the second part, that is r power 1, r power 3 and so on, r power p minus 2 are set of all quadratic non-residues modulo p. Hence, we have that r power 1 into r cube, r power 5 and so on, which is equal to r power 1 plus 3 plus 5 and so on plus 2 into p minus 1 by 2 minus 1. That is sum of, this is as we proved earlier in chapter 1, that this 1 plus 3 plus 5 plus and so on, this is it is a square number. So, that is p4 of n. So, this is equal to r power p minus 1 square by 4. We introduced quadratic residues and quadratic non-residues, and we also showed, stated and proved Euler's criteria to that going to give us whether given number is a quadratic residue or not. Now, we are going to establish that minus 1 is a quadratic residue modulo p whenever p is of the form 4k plus 1. Consequently, we will show that a and minus a are quadratic residue modulo p whenever p is of the form 4k plus 1. We are also going to introduce a symbol called Legendre symbol, and we will going to prove various properties of this Legendre symbol. And finally, we are going to show that there are infinitely many primes of the form 4k plus 1. Now, we are going to introduce a Legendre symbol. It is the definition is like this: let p be an odd prime and a is a natural number such that GCD of a comma p equal to 1. The Legendre symbol is denoted a by p, which is defined as a by p equal to 1 if a is a quadratic residue modulo p, and a by p equal to minus 1 if a is a quadratic residue non-residue modulo p. So, some of the properties of this Legendre symbol, let P be an odd prime, let A and B are two integers that are relatively prime to P, then the Legendre symbol satisfies the following properties. First one is, if A is congruent to B mod P, then the Legendre symbol A by P is equivalent to Legendre symbol B by P. That means both A is a quadratic residue modulo P and B also quadratic residue modulo P, or both are quadratic non-residues modulo P. So, this happens whenever if A is congruent to B modulo P. The next result is A square by P is equal to 1, that is the Legendre symbol A square by P is always 1, that is A square, it is easy to see that A square satisfies x square equal to A square modulo P. So, A square is always a quadratic residue modulo P for any prime P. So, that is why A square by P is equal to 1, and A by P is congruent to A power P minus 1 by 2 modulo P. That is by this is comes from the Euler's criteria. If A is a quadratic residue, then A power P minus 1 by 2 is 1. If A is a quadratic non-residue, we know that A power P minus 1 by 2 value is minus 1. So, that is related to the Legendre symbol. Another result is 1 by P. So, that is 1 is always a quadratic residue modulo P for every prime, and minus 1 by P is equal to minus 1 whole power P minus 1 by 2. So, now we are going to prove these results one by one, and another result is A by P is equal to A by P into B by P. This says that once you fix the prime P, then Legendre symbol acts like a completely multiplicative function. Actually, Legendre symbol has two arguments, A as well as P, but once we fix P, then it has only one argument. So, it is a mapping from natural numbers to real or complex numbers. In particular, its values are 0 or 1 or minus 1. So, it is a number theoretic or arithmetic function. Further, this last property says that this is also a completely multiplicative function once we fix the prime P. So, the proof goes like this. First one, if let us assume that A is congruent to B mod P, or this is also equivalent to A is equal to B plus Kp for some k belongs to Z. Hence, x square equal to A mod P as solution if and only if x square is congruent to A, which is equal to A plus Kp, which is congruent to B modulo P. Thus, A by P is equal to 1, that is A is a quadratic residue modulo P if and only if B by P is equal to 1, B is a quadratic residue modulo P, or equivalently A by P equal to B by P. Clearly, the equation, that is what we already mentioned, x square equal to A square mod P has a solution plus or minus A. So, A square by P is always equal to 1. Now, by theorem Euler's criterion, by theorem 3 which we proved earlier, A is quadratic residue modulo P if and only if A power P minus 1 by 2 is congruent to 1 mod P. Also, A by P is 1 if and only if A is a quadratic residue modulo P. Hence, we have that A by P Legendre symbol is congruent to A power P minus 1 by 2 modulo P. Now, the other parts follows from previous statement. Now, we are going to prove the last property. We know that AB is a quadratic residue modulo P if and only if either both A or B quadratic residue modulo P, or both A and P are quadratic non-residue modulo P, or equivalently both A by P, B by P 1, or both A by P and B by P minus 1. That is why we are going to get AB by P is equal to A by P into B by P. In other words, Legendre symbol is completely multiplicative once P is fixed. Now, we are going to show another important property of this Legendre symbol, that is, if P be an odd prime, then summation A is equal to 1 to P minus 1, A by P is equal to 0. This follows very easily, since because there are exactly P minus 1 by 2 quadratic residues and P minus 1 by 2 quadratic non-residues. and then we are going to evaluate minus 1 by p, which is equal to 1 if p is equal to 4k plus 1, or minus 1 if p is of the form 4k plus 3. So, now we will prove the first part. Since p is an odd prime, so by previous theorem, that is Euler's criteria, the number of quadratic residue modulo p and number of quadratic non-residue modulo p both are equal to p minus 1 by 2. Thus, the numbers 1 and minus 1 appears exactly p minus 1 by 2 times. That is why we are going to get summation a equal to 1 to p minus 1 a by p, b equal to 0. Now, proof of the part 2. Now, in the previous result we proved that minus 1 by p is equal to minus 1 whole power p minus 1 by 2, and so obviously this p minus 1 by 2 becomes even, then we are going to get minus 1 by p, or minus 1 becomes a quadratic residue modulo p, that we require that p minus 1 by 2 equal to 2 into k. So, that is same as p is equal to 4k plus 1. Thus, this is an important thing, that minus 1 is quadratic residue modulo prime p if and only if p is of the form 4k plus 1. Now, we will going to solve one simple problem. Let p is an odd prime dividing 9 power n plus 1 for some integer n, then we can prove that p is congruent to 1 mod 4. Let p be an odd prime dividing 9 power n plus 1, that is, then we have that 9 power n plus 1 is congruent to 0 mod p, or equivalently 3n whole square is congruent to minus 1 mod p. So, from this what you can observe is that minus 1 is a quadratic residue modulo p. So, from the previous result, minus 1 is quadratic residue if and only if p is of the form 4k plus 1. So, that is why if whenever p divides 9 power n plus 1, then p has to be has of the form 4k plus 1. Now, we are going to show that there are infinitely many primes of the form 4k plus 1. So, the statement is like this: there are infinitely many primes of the form 4k plus 1. Earlier we showed that Euclid proved that there are infinite number of primes, but there is no restriction. Out of all the natural numbers, we tried to find how many primes are there. We showed that there are infinite number of primes, but we cannot generalize that proof here. Earlier we also proved that there are infinite number of primes of the form 4k plus 3 as well, but this proof that there are infinite number of primes of the form 4k plus 1 is not that easy to prove without using quadratic residues. That is why its proof is now postponed. Now, we are going to prove this. Now, by using quadratic residues, this can be proved very easily. So, now again proof is follows in the same lines as general proof that the number of primes are infinite. Let us suppose that there are finitely many primes of the form 4k plus 1, that is say p1, p2 and so on pn. All these are of the form 4k plus 1. p1 is of the form 4k plus 1, p2 is of the form 4k plus 1 and pn is of the also prime of the form 4k plus 1, and these are the only primes of the form 4k plus 1. Now, we need to show that we need to produce a new prime other than these. So, for that we are going to consider a number n which is equal to 2 times p1, p2 and so on pn whole square plus 1. Recall that similar to this we proved that number of primes are infinite. There we assumed that p1, p2 and so on pn are the primes, then we consider n is equal to p1, p2 and so on pn plus 1. But here we are considering n is equal to 2 times p1, p2 and so on pn whole square plus 1. Then clearly n is greater than 1. So, by fundamental theorem of arithmetic, n has a prime factor. So, further n is also odd. So, it has to be divisible by an odd prime p. Hence, and so once p divides n, but n is equal to 2 into p1, p2 and so on pn whole square plus 1. So, we are going to get 2 into p1, p2 and so on pn whole square is congruent to minus 1 mod p. That is, it says that minus 1 is a quadratic residue modulo p. So, the by some previous result we showed that minus 1 is a quadratic residue if and only if P is of the form 4k plus 1. So, P is now of the form P is congruent to 1 mod 4. Now, clearly P cannot be one of the Pi. If P is one of these Pi, then what happens? Pi divides 2 into P1, P2 and so on Pn whole square, and also so P divides Pi divides n also. So, Pi divide their difference, that is Pi divides 1, which is a contradiction. That is why this prime has to be different from one of these primes P1, P2 and so on Pn. Hence, we got the required result. So, let P be a prime with P is congruent to 1 mod 4, then verify that the sum of quadratic residue modulo P lie in the set 1, 2, 3 and so on P minus 1, which is equal to P into P minus 1 by 4. The proof is simple. Let A1, A2 and so on AR be all the quadratic residue modulo P that are less than P by 2. Since P is congruent to 1 mod 4, minus 1 is a quadratic residue, hence P minus A1, P minus A2 and so on P minus AR also, they are also quadratic residue modulo P, but they are greater than P by 2. So, the number of quadratic residue modulo P are equal to P minus 1 by 2. We see that R is equal to P minus 1 by 4. Thus, the sum equals to, that is sum is I is equal to 1 to R AI plus sum is I is equal to 1 to R P minus AI, which is equal to simply sum I is equal to 1 to R P. So, that is P times into R. So, that is equal to, but R is equal to P minus 1 by 4. So, we got P into P minus 1 by 4. So, what we showed is sum of quadratic residues modulo P whenever P is of the form 4k plus 1 is P into P minus 1 by 4. So, another problem is, let P be an odd prime and A comma B are natural numbers such that GCD of AB comma P equal to 1, then exactly one of A or B or AB is a quadratic residue modulo P. So, this is easy to show, and so we are leaving that as an exercise. Let another problem is, let P be an odd prime, then show that there are exactly P minus 1 by 2 minus P of P minus 1 quadratic non-residues which are not primitive roots modulo P. So, for any odd prime P, there are exactly 1 by 4 times P minus 4 minus 1 whole power P minus 1 by 2 consecutive pairs of quadratic residues will exist. That means both are quadratic residues. The proof goes like this: if both k and k plus 1 are quadratic residues, then Legendre symbol k by p is equal to k plus 1 by p, which is equal to 1. Otherwise, 1 plus k by p or 1 plus k plus 1 by p is 0 if one of them is not a quadratic residue. Hence, the number of consecutive pairs of quadratic residues is 1 by 4 times summation k is equal to 1 to p minus 2, 1 plus 1 by p into 1 plus k plus 1 by p. So, if we simplify and if we use the fact that earlier proved result, summation a is equal to 1 to p minus 1 a by p is 0, then we will get the required part, that is we will get x value by simplifying this. So, we can show that the required answer is going to be 1 by 4 times p minus 4 minus 1 whole power p minus 1 by 2. Now, we are going to try to solve this equation, whether it is solvable or not we need to find out, that is x square is congruent to 73 mod 173 is solvable or not. Actually, as recall that we started to answer questions of this type. So, the first note that x square equal congruent to 73 mod 173 is solvable if and only if 73 is quadratic residue modulo 173. So, finding solution to x square congruent to 73 mod 173 is equivalent to finding 73 is a quadratic residue modulo 173 or not. So, but 73 by 173 Legendre symbol, which is equal to minus 100 by 173, but 100 minus 100 is nothing but minus 10 square, but 10 square is always a quadratic residue. So, which is equal to minus 1 by 173, and but 173 is a prime of the form 4k plus 1. So, minus 1 is a quadratic residue. So, 73 by 173 is equal to 1. So, we showed that 73 by 173 is same as minus 1 by 173, and 173 is of the form 4k plus 1. So, that x square congruent to 73 mod 173 has a solution. As we showed, minus 1 is a quadratic residue modulo p if and only if p is of the form 4k plus 1, and we showed and we defined and showed various properties of Legendre symbol in this module. Legendre symbol behaves like a Mobius function which takes values either 0 or 1 or minus 1. It takes value 0 whenever p divides a, that is Legendre symbol a by p is equal to 0 whenever p divides a, otherwise it takes values either 1 or minus 1. And later we showed that there are infinite number of primes of the form 4k plus 1 by using quadratic residues. If we do not use quadratic residues and we want to show an independent proof, then it becomes very lengthy. By using quadratic residues, the proof becomes very easy, and that is why we showed the number of primes of the form 4k plus 1 are infinite now. With this we end this module.